Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, Mr. Nofri. Good morning, everyone. We are from Group 6, Class Stochastic Process K. Here we are gonna present about the ATM machine queue problem. Next. Okay, let's meet our team. The first one is Farah Diva with last NRP 134, and then Shafina Nur Rizqilliany with last NRP 135, and then Arya Rachman Setiadi with last NRP 147, and me, Aisha Zahra Inayatullah with last NRP 184, and there is Kezia Aimee Boengai with last NRP 187. Next. Okay, question number 1. Define the states of the Markov chain and the transition rates between the states and draw the rate diagram. State xt represent the number of a customer at the ATM at time t, with xt the member of 0, 1, 2 until 10. And the state space is from 0 until 10. And the state 10 is a customer at the ATM and there is a maximum capacity. And thus the state space is from 0 until 10. Okay, next. And then there is a transition rates between these stats are determined by the arrival rates of a customer is a lambda and the service rate is a mu. And there's a customer arrival. There's a 3 point about the customer arrival. There is a new customer arrive at the ATM at a rate of lambda. And there is a transition from xt equal to n to xt equal to n plus 1 occurs at a rate of lambda for n equal to 0 until 9. And the last is if the ATM is full, so xt equal to 10 and no new customers are accepted. And the second is a service completion and there is a tip. The first one is customers are served at a rate of mu. And the second one is a transition from xt equal to m to xt equal to n min 1 occurs at a rate of a mu for n equal to 1 until 10. And the last one, if there are no customer, xt equal to 0 and no service occurs. And the capacity limit is the maximum state is 10 customer. And if the ATM is full, xt is equal to 10 and there is no transitions to n plus 1. Markov chain properties. The system is a continuous time Markov chain because the time between transitions follow an exponential distribution and the transitions depends only on the current state and not on history. Next. So this is the rate diagram that I got from the software of our studio. The lambda, it means arrival rate of customers and mu is a service rate. Next. Okay. Question number 2 is derive the rate matrix and generator matrix for the CTMC. Matrix Q has a dimensions of 11 multiplied 11 corresponding to the number of states in the system is xt equal to 0 until 10. Of the general elements, there is a 2. There is arrival rate. The lambda is 0.5 and the service rate is a mu 1.0. And the general elements is the negative sum of all non-diagonal elements in that row. And the properties of the generator matrix is a row sum property and the sum of the elements in each row equals 0. Next. And this is the matrix that I got from software RStudio. And the conclusion is the generator matrix Q is aligns with the definition of a CTMC for the ATM queuing system. And this matrix illustrates the transitions between states with a parameter lambda, arrival rate, and a mu, the service rates. Okay, next. Okay.
Okay, next number 3 is visualize the distribution. There is service time distribution. The service time distribution is checklist to the right, indicating that most transactions are completed quickly within a short duration, while a smaller number of transactions take longer. And the second one is inter-arrival time distribution. The inter-arrival time distribution is also right, suggesting the most customer arrive at the ATM in quick succession, short inter-arrival times, while no longer gaps between customer arrival are less frequent. Next. Number 4 is average inter-arrival time and the service time. The average time taken to serve a customer is 238.454 seconds. And the second one is the average time between the arrival of two consecutive customers is 308.74 seconds. The fact that the average service time is shorter than the average in the arrival time because the customer are arriving at a rate that allows for adequate service without excessive waiting. However, if the service time were to increase of if the inter arrival time were to decrease, it could lead to a situation where customers begin to queue, especially during peak hours. This balance is crucial for maintaining an efficient and customer-friendly ATM service. Next.
So for questions number 5 is estimate the parameter. The first one is the likelihood function for arrival rate. The parameter lambda represents the arrival rate of each customer to the ATM, which is the average number of customers arriving per unit of time. So the probability density function of the exponential distribution is given as follows. And then for inter-arrival time data, T1, T2 until Tn, the likelihood function is as shown as the screen. Next, to simplify the calculation, we use the log likelihood function. And then to maximize the likelihood, take the derivative of ln L lambda with lambda and set it equal to 0. Next. So the equation obtained is as follows. The average inter-arrival time of customers is found to be 309.049 seconds. The calculation for the arrival rate is obtained, which is the average arrival per unit of time. The exact value of the parameter lambda can be calculated using the time between arrivals. So the parameter for the arrival rate is 1 divided by mean arrival time. So 1 divided by 309.049 equals to 0.0032. Next is estimate the parameter, the likelihood function for service rate. The parameter mu represents the service rate of the ATM, indicating how many customers can be served per unit of time. So the probability density function of the exponential distribution is given as follows. Next, the likelihood function for the service previous page. The likelihood function for the service duration S1, S2 until Sn is as shown as the screen. Next, to simplify the calculation, the log likelihood is used. And then to maximize the likelihood, take the derivative of the ln L mu with mu and set it equal to 0. Next page. So the equation obtained is as follows. The average service time of the server over 24 hours of ATM usage is found to be 238.454 seconds. So the calculation for the service rates obtained, which refers to the average service time. The exact value of the parameter mu can be calculated using the service duration time. So the parameter for mu is 1 divided by mean of services time. So 1 divided by 238.454 is equals to 0.0049419. Next page. Okay, so for question number 6, suppose that one day at 5 a.m. the ATM queue is empty. Calculate the probability that there are K people there at 7 a.m., K 1 until 10, 0 until 10. Calculate for each K and calculate its expected value. So the probability function is as shown as the screen. And the nodes P and T equals to K is the probability of K people arriving within time T. Then for lambda is the arrival rate, T is the time duration with second, and K number of the customers. And then the expected value of E and T for the number of arrivals within time T within time t is lambda t. Next. Okay, so by performing the calculations using the syntax in Python, the following results were obtained. So for the probabilities of having k customers at 7 a.m., P0 equals to 0.0026, P1 equals to 0.0155, P2 equals to 0.0466, P3 equals to 0.0932, P4 equals to 0.0932, P4 equals to 0.1398, P5 equals to 0.1678, P6 equals to 0.1678, P7 equals to 0.1438, P8 equals to 0.1079, P9 equals to 0.0719, and P10 equals to 0.0431. And the expected number of customers at 7 a.m. is 5.7411, so it equals to 5 customers.
Next, number 7, suppose that the ATM machine is idle at 8 a.m. What is the expected amount of the time the machine is idle during the next hour? Now, so first step is define lambda. Lambda is arrival per second. The lambda equals 0.01158. Next step is define mu. Mu is service completed second. Value from mu is 0.0441. Now we can find the steady state. Here is the formula from P1. Value from P1 is 0.0631. Now the next step is find the expected time when the machine idle for 1 hour. The formula from expected idle time is P1 times 368 3,610. The value of the idle time is 3 minutes. Now number 8, compute the limiting distribution of the state of the ATM queue. The first step is define the state space. The state space is 0 until 10. Now define lambda. Lambda is arrival per second. The value from lambda is 0.01158. Next step is define mu. Mu is service completed per second. The value from mu is 0.0419. Next step is calculate limiting distribution with formula. Here is the formula. Now the next step, compute the limiting distribution that we compute from the output from the language. Now, number 9 will be explained by my friend.
Okay, so for the number 9, the question is let the initial investment in the ATM I is $15,000 and the annual maintenance cost is M is $1,500. The total annual operating cost includes first one is electricity cost per year, with CE is $1,200 per year, and the second one is transaction processing cost, or CT, is $0.25 per transactions, and the calculate the annual profit and the ROI if we charge the customer the transaction fee with 3 different scenarios. The first scenario is $0.5, and the second one is $1, and the third one is $2 for each transaction. So this is the output from Python that we use. Next. From the output, we can conclude that the calculation shows that the annual profit and ROI of the ATM increase with higher transaction fees. At a fee of $0.5, the annual profit is can be seen dollars with an ROI of 200 and 14.16% with a fee of $1. The profit raises to can be seen dollars and ROI to 678.48%. And the $2 is the highest profit of $241 and RIE of 1,016.07.11% is achieved. Higher transaction fees lead to greater profits and ROI. Next. So the conclusion is this report analyzed the operational performance of an ATM machine using the continuous time Markov chain, or we can call it CTMC model. The results demonstrate that the operational efficiency of the ATM can be optimized by understanding QA dynamics and usage patterns. Analysis of various transaction fee scenarios indicates that increasing the transaction fee leads to higher annual profits and returns on investment, or we can call it ROI. So overall, the CTMC model provides valuable insight for enhancing the design and management of ATM system to achieve a balance between customer satisfaction and operational profitability. Next. So thank you for your attention and thank you for Mr. Nofri. I think that's all from our group 6. Thank you.